My name is Scott Wiedemann. I'm a student at Colorado School of Mines. This is a presentation I gave for a class Cheminformatics on graph isomorphism and subgraph isomorphism. I'm going to make this available on YouTube for anybody to enjoy. This is one of two videos that I'll put up. The other video will be about encodings, inchi and smiles, and some of the namings of chemical compounds. So during this presentation, I'm going to talk about chemistry and graphs and sort of the background behind the computer science and chemistry merging together, and what that means and why that's important to these two problems. Graph isomorphism and subgraph isomorphism will be the main topics that I'm talking about. So I'm going to refer to them as GI and SI. So if you hear me say GI, that's the graph isomorphism problem, and SI, which is the subgraph isomorphism problem. And those are two distinct problems, so do not confuse them. Talk about how these are relevant to cheminformatics. These problems are traditionally sort of in the computer science domain. I'll give a formal definition. Both of these are well-studied problems, so it'll be easy to go over them, and there's an infinite amount of information on these problems if you want to know more. And then, we've sort of talked about why these problems are difficult in class, or what makes these problems difficult. Well, we've sort of been ignoring that, so we're going to talk about why these problems are hard. And to do that, we're going to talk about some complexity classes, P, NP, NPC. We're going to prove that the SI problem is in NPC, and any bold text on slides indicates that it'll be on your quiz. So there's some questions at the very end of this presentation, and bold text throughout the presentation is an indication that that information will appear on the quiz. So some applications to chemical structures. So when I talk about mapping a chemical structure to a graph, so this is the merge between computer science and chemistry here. So a chemical structure, some compound, when we think of that, that's a real thing, some atoms and molecules. And when we see different representations, whether it be a stick and ball picture on this slide, or a 2D representation, any sort of encoding, it's a representation to us. And a natural way to encode this as a graph in computer science, is that the atoms of a compound represent the nodes, and the bonds between atoms represent the edges. So there are definitely other properties that we could capture in a compound, say the type of atom, maybe it's carbon or hydrogen, oxygen, the charge, maybe the overall charge of something, so degree of a bond, whether it's maybe we could have a weighted edge in a graph that might indicate the degree of the bond. But really, really the representation of a graph is just dependent on how much information we want to capture. So minimally, we're gonna say the atoms are nodes and the bonds are edges. A graph is pretty boring if it doesn't have any nodes. So some problems that arise in cheminformatics and chemistry is determining if two chemical structures are the same. So you're given two representations, whatever that may be, and you need to determine whether the structures are identical. And in computer science, that sort of translates to this subgraph, or to the graph isomorphism problem. Does a chemical structure contain a given substructure? Well, that's the subgraph isomorphism problem. So these are two distinct problems, graph isomorphism and subgraph isomorphism, and they have distinct applications on the chemistry side. So we can use that mapping of a chemical compound to represent these as a graph, and then we've sort of done the conversion of one question into another question. So solving the graph isomorphism problem would give you the answer to are two chemical structures the same? assuming that you can do the mapping from the chemical structures to the graph. So a formal definition of the graph isomorphism problem is given here, but before we define that, it's important to know what a simple graph is. A simple graph is an unweighted, undirected graph containing no graph loops or multiple edges. The formal statement for the graph isomorphism problem: let V of G be a vertex set of a simple graph G and E of G its edge set. Then a graph isomorphism from a simple graph G to a simple graph H is a bijection F of V of G to V of H such that the edge UV within the set E exists if and only if the mapping of that edge, so the bijection UV, is in the other edge set H. So that basically says, hey, two graphs are isomorphic if there's a permutation of the vertices which transform one graph into the other, preserving the edges. And that's more intuitive to look at a picture. So these two graphs that you see, the one on the left and the right here, are isomorphic to each other. The one on the left is encoded with letters, the one on the right with numbers. The color of the node from one graph to another is consistent, but the letters and numbers are not. So you can sort of do a mapping in your head here that A maps to 1 and H maps to 2, G maps to 5, right? And you can verify that the edges here and nodes map correctly. Now, you'll also notice, it's a little bit easier to see with the graph on the right, but you also notice that the graph is symmetric in many directions. Horizontally, vertically, you could replace the inner four nodes with the outer four nodes and you'd still have a symmetric graph. So that is to say that there's more than one solution to graph isomorphism, to say, okay, this representation and this representation are isomorphic, but how many representations are there? So that's something just to keep in mind. The subgraph isomorphism problem, different problem. You can sort of think of it as a generalization of the graph isomorphism problem. So given two simple graphs, G and H, does G contain a subgraph that is isomorphic to H? These two pictures illustrate that with the graph on the left and right here. You can see that the edges in red on the graph on the left have a subgraph that's isomorphic to the graph on the right. In order to talk about why these problems are hard or difficult to solve, we need to talk about complexity classes. And complexity classes are sets of problems, classes of languages. So you'll have many different problems in computer science, whether it be shortest path or minimum spanning tree. Any of the problems that you might be familiar with fall into these complexity classes. P, NP, NPC, and NP-hard. So we'll talk in detail about how these classes relate to each other, what it means to belong to a class, and what the class really defines. P is the set of problems that can be solved in polynomial time. So P contains decision problems, and a decision problem is a question with a yes or no answer, and that's sort of the dual of an optimization problem. So you can have a decision problem and an optimization problem. A decision problem has that yes-no answer. An optimization problem, you're trying to optimize something if it wasn't intuitive enough. And there's a conversion that can be done from an optimization problem to a decision problem. And you're probably more familiar with optimization problems, which is like, find the shortest path in this graph between nodes A and B, right? While you're trying to optimize something, you're trying to actually find the shortest path. It doesn't have a yes-no answer. But you could convert that problem to a decision problem by saying, is there a path with length k in this graph from node A to B? And then you could sort of reduce k. And that question has a yes-no answer and is a decision problem. So it's important to know the difference and make the distinction and sort of realize that most optimization problems can be phrased as a decision problem. So P contains all decision problems which can be solved by a deterministic Turing machine using a polynomial amount of computation time. Well, that's a whole bunch of CS lingo to say, hey, your problem can be solved, or there's somebody's found a way to solve this problem in polynomial time. So when I talk about polynomial time, I'm saying big O notation. So big O notation of n to the k. So n is some variable of the input size, and k is a constant in this case. So maybe n is the number of nodes, or n is e plus v, or some representation of the input to your problem. K is a constant. So an example, like I sort of stated before, shortest path would be an example. You can use Dijkstra's algorithm, which runs in polynomial time to solve the shortest path problem. And remember, you could phrase shortest path as a decision problem and not an optimization problem. When you think of P, think of n to the k. So n is variable on the input, and k is a constant. So that's P. P, as you can see on the right, is a subset of NP. And NP will be the next class we talk about. So NP is a class of languages that can be verified by a polynomial time algorithm. So what does it mean to be verifiable in polynomial time? So for something to be verifiable, you need to provide sort of like a certificate or some sort of solution to the problem almost. So I'll give an example. Shortest path, for example. If you're finding the shortest path between nodes A and B, that can be done in polynomial time P. But to verify that something is the shortest path between A and B, you could provide the shortest path, say a list of edges and nodes, and also run through the graph in polynomial time and check to say, oh, hey, this answer is the shortest path, right? So that's not a great example, because shortest path can be solved in polynomial time anyways. But there are some problems. Consider Hamiltonian cycle, or maybe the traveling salesman person problem. Different problems, but similar. Consider those problems and say, okay, well, let's say they can't be solved in polynomial time, so there's not an algorithm to do it in polynomial time, but can I verify it? Can I verify that the solution to the traveling salesperson problem is the right solution in polynomial time? If that seems confusing right now, that's okay. It'll clear up when we talk about NPC. But think of NP as I can verify something in polynomial time. So NPC, problems that belong to this class simply mean that no polynomial time algorithm has been discovered yet. And we think of problems that are in NPC where the input size is in that exponent. So you see this big O notation, k to the n is that input. So this could take a ridiculous amount of time, for an input size of 1,000, and even if k is 2, right? 2 to the 1,000 is massive. So this could take a long time for even relatively small inputs. An example of a problem that's in MPC is Boolean satisfiability, or SAT as I'll call it. And this problem was one of the only problems, the first problem to be shown to be in PC. And so smart guy by the name of Cook in the 70s, went to Harvard, did a lot of math, spent a lot of time proving that this problem that he could formally state, this Boolean satisfiability problem, was an NPC. So now that we know that this SAT problem is in NPC, we can prove other problems are in NPC by reducing them to that problem, so sort of equating them. So you might have a different problem and you want to prove that it's in NPC. Well, if you can transform that problem sort of into the problem that you know to be NPC, and likewise transform the NPC problem into your problem, then you can say, okay, this problem is in an NPC. For the same inputs, I get the same outputs. It's important to phrase the problem that you're trying to show that's in MPC as a decision problem. So MPC contains decision problems, just like P contained decision problems. There's a lot of literature and text on whether P and NPC are complete. If a polynomial time algorithm was discovered for an NPC problem, then basically all problems in NPC could be solved in polynomial time. And that's because we did do that equating of the problems in NPC to each other. So if all problems in NPC can eventually be equated or sort of reduced to this SAT problem, and SAT can be solved in polynomial time, well then all problems in NPC can be solved in polynomial time. This slide just has a lot of examples of problems in NPC. You may not be familiar with a lot of these problems. You know, day to day, you're familiar with problems in P. These are the problems you're common with. If you're a coder, if you program and you're solving problems, writing algorithms, you're usually familiar with problems in P. Problems in NPC, on the left here, there's 21 problems over here. Satisfiability at the top, which is the one I talked about on the previous slide. The other problems on the left here, Karp, a guy named Karp who's also working with Cook, wrote a paper and did these reductions and proofs that all these problems can reduce to their parent. So I have sort of a tree structure over here on the left. So for example, 0-1 integer programming, that was shown to be equivalent to satisfiability and therefore in MPC. So you can see a lot of problems over here that you might have heard of: graph coloring, subset sum, Steiner tree, vertex cover. So these are pretty basic and famous problems in NPC. The problems on the right here, just some more problems I wanted to list: bin packing, knapsack, independence set, other problems that you might be familiar with. The halting problem is in pink there because that problem is actually unsolvable. There's a set of problems that are in NP hard, and let me go back to this slide. In NP hard, you'll see that those problems are harder than any problem in NPC. You'll notice that they aren't in NP as well. So meaning the problem is so hard it can't even be verified in polynomial time. So to verify it is harder than doing that. So harder than any problem in NPC, and it's not in NP. So there are definitely NP hard problems, and we can show that they're in NP hard, but there are also problems that are unsolvable too. I won't get into that, but definitely something that's interesting to take a look at on your own. Let's get back to showing that graph isomorphism and subgraph isomorphism fit somewhere into these classes. So graph isomorphism is in MP, meaning it can be verified in polynomial time, but no known algorithm there's no known algorithm in P for graph isomorphism. But it hasn't been shown to be in NPC, so it's sort of a special problem. It sort of sits in between P and NPC in this picture on the right here. It's an odd problem, and there's not a lot of problems that are like this. It's unique, and people have spent a lot of time looking at this problem and trying to show it one way or the other. And it's in a class of problems that I'm going to call GI. So this GI in bold here, that's not to be confused with the problem itself, but a class of problems. So it's sort of like the graph isomorphism complexity class, right? And likewise, there would be GIC and GI hard, which would be complementary complexity classes to those of NPC and NP hard. So you can sort of imagine if we were to put another parabola here and another little circle where P and NPC and NP hard exist, of GI, GIC, and GI hard. And so there are problems, that are equivalent to the graph isomorphism problem, which are said to be in this GI set, so the GI class, excuse me. And so remember, those would be sets of problems with polynomial time turning reduction to the graph isomorphism problem. And there are several problems like this or similar to this, and problems that also exist in GIC and GI hard. You might be familiar with digraphs and multigraphs and hypergraphs, and they fall into some of these computation classes. So graph isomorphism is an interesting problem. It's not as traditional as some of the other problems. There are special cases of graph isomorphism. So if your graph is a tree or a planar graph, it can be shown to be planar, or interval graph, maybe it's partitionable among k trees, or it's bounded by certain constraints. So your graph might be bounded by a degree or the genus. And these special cases, there may be a polynomial time algorithm. So, if your graph is a tree, then there's an algorithm to solve that in P. I don't want to say that about all of these other special cases, but when you constrain the problem by constraining the degree or the bound or some of these other features of graph, it usually gives you a leg up in your algorithm. You can usually take advantage of that. Now, the funny thing about the bounded genus and degree, there's been a proof somewhere that says, theoretically there should be a polynomial time algorithm to solve the GI problem in the case where the graph is bounded by degree, but nobody's been able to code it. I don't know if people are lazy or what, but nobody's been able to code this thing. So it may be impossible to code, but theoretical to prove that a problem should exist. When we think about our case of a compound, a compound has weighted edges possibly, and some node types, and some other sort of constraints. If we were to constrain our problem, it still makes the problem hard. So it's still a difficult problem. Let's talk about subgraph isomorphism. That's a little more straightforward. We can show that that problem is actually in NPC. So let's refresh ourselves on the problem. G contains a subgraph that is isomorphic to H. So given two graphs, does G have a subgraph? That's isomorphic to H. To prove that it's in P, let's let an instance of the problem be that input GH that I was talking about, two graphs. Your certificate can also be an input. Remember, we're trying to show that it's verifiable in polynomial time. So the certificate could be a list of nodes in GX. It's important that it's a list here, not a set, so an ordering of nodes. You could prove that the list is indeed a solution to the problem by saying, okay, for two entries in the list, xk and xl, verify that the edge xk, xl exist in edge set 1 if and only if the index kl exists in edge set 2, where edge set 1 and edge set 2 respectively come from graphs G and H. And that would take big O of n squared time, where n is approximately the size of the graph G, or related to the number of nodes in G. So it is indeed verifiable in polynomial time, which means it's in NP. So SI is in NP. It's our first step to showing that a problem is in NPC. To prove that SI is in NPC, we're going to transform a problem called click, which is known to be in NPC. It's one of the problems that that I had listed earlier, CARP's 21 problems. And click is the problem where you're trying to find the largest fully connected subgraph within a graph. So you can see this image on the right here shows sort of some iterations. We're going through this graph and looking at 4 nodes at a time in this depiction. And the last little image here shows 4 nodes fully connected, which we would call a click. So a click of size k, or of degree k, in this case 4, So there are 4 nodes that are fully connected in this graph. So we would say this graph has a clique of size 4. It may have a clique of 3 and undoubtedly 2. And so you can see how clique is similar to our problem in that we have a subgraph and a bigger graph, and we're looking for sort of connectedness and edges here. So we're going to transform this problem clique, which we know to be an NPC, to our problem, SI subgraph isomorphism. To prove that SI is in NPC, we're going to create an instance of the subgraph isomorphism problem with just 2 graphs here, G and G sub K, but G is the graph of concern, and G sub K is a fully connected graph of degree K, a complete graph of degree K. So we can construct that instance in polynomial time. We can say these 2 instances are equal if we can show that the clique problem equals this instance of SI that we made, and if the SI instance we have is equal to an instance of clique. So if G has a K clique, then G has a complete K graph as a subgraph. And the instance G sub K is also a yes instance. If G has G sub K as a subgraph, then it has a K clique as a subgraph, and hence G comma K is a yes instance of clique. Well, that's true also by design, right? We built an instance of subgraph into our graph isomorphism problem. So G sub K is the other graph in the graph isomorphism instance, the second graph in the input. And then in the clique problem, we're looking for a graph of size K. Well, that's the input, that's the input to the problem. So those 2 are equivalent. And this is by no means a formal definition at all, but you can go ahead and probably prove to yourself that these 2 problems are equal to each other. So for now, we're just going to say, yes, SI is in NPC. We showed that by reducing the clique problem. Now that we know SI is in NPC, how do we deal with it, right? So that means there's not an easy algorithm to solve it. It's going to take a long time because the size of the input, even for a relatively small graph, is in that exponent. This graph on the right here, you can imagine taking this, which is not an extremely complex structure, but we can take this, encode it as a graph, and then try and run subgraph isomorphism on a number of different compounds. You can see how that would get very costly very quickly. And so to deal with problems that are in NPC, normally other problems, usually have an approximation algorithm. An approximation algorithm, it'll find a solution within a factor of optimality. So you can say, here's my problem here, and this is an instance of my problem, right? The optimal solution is this, and so you sort of know what the optimal solution is. You have these designs of structures of your problem, and you're saying, here's an algorithm that doesn't solve it exactly, right? But it approximately solves it. So the solution to the problem is approximate. So we're talking about the quality of solution when we talk about approximation here. So there are approximation algorithms that we can use if needed, and we could take advantage of some of those constraints as well that may help us. And a lot of problems are usually constrained. Subset sum, that's a problem, and which is known to be NPC for numbers that are not restricted on the domain. But if you're dealing with bounded integers, for example, then it is possible to solve the problem. So a lot of times you can take advantage of these constraints. Some of the things that we've seen in this class, Cheminformatics, to deal with this subgraph isomorphism problem, we've gone through fingerprinting and canonical naming of compounds and structures. And that is an effort to deal with some of this stuff, I think. If the canonical naming problem were solved and we could give a unique identifier to every compound we encounter. Well, that's pretty similar to graph isomorphism. If we can represent one graph and another graph with this unique identifier, let's say the graphs are isomorphic to one another, and we can generate a string, a unique string that says, hey, this thing and this thing map to this same value, then we sort of would have solved that problem. So there are these things in cheminformatics that are maybe a little less formal from a computer science standpoint, but deal with very similar problems. I hope throughout this presentation you have a better understanding of our two problems, graph isomorphism and subgraph isomorphism. You recognize that the problems are tough. Subgraph isomorphism is in MPC. You have a better understanding of complexity classes, I hope. If you have any questions, feel free to leave them in the comments of this video, and I will show the quiz questions now. Check out my second video. It's going to talk about smiles and inchi, which are encodings of compounds. Yeah, I'll put a link in the comments for that as well. Thanks.